Welcome. In this class, let us start looking at temperature profile in a tissue. Okay. As we go through this, see whether you're reminded of something else that we did earlier in the course. Okay. At some point in time, it will be quite apparent. Till then, at the back of your mind, keep seeing whether this is somewhat similar to something else that we did in the earlier part of the course. To do this, as we have been doing in this course, problem-based learning and so on, I'm going to present a problem, then solve it, give you the principles for solving it as or in the context of solving this problem. And that way the learning is expected to be much better. So the problem reads as something like this: find the temperature profile and the maximum temperature attained in a tissue at steady state. Highly relevant, right? A tissue or muscle maybe, caused by heat generation due to metabolism. Say, attained in a tissue caused by the heat generation generated due to metabolism. Okay. This is what we're going to look at in this class. For that, let us approximate the tissue to be a cylinder of radius r and thermal conductivity K, and with a uniform constant heat generation Qm dot. Okay. There's a there is a tissue, let's say muscle tissue, a lot of blood supply to it and so on and so forth, right? And a lot of metabolic processes going on, biochemical processes going on. There is a lot of heat generated because of those reactions, okay? And that is what we are going to call as Qm dot, metabolic heat generation rate, and we're going to take it as a constant in this case. Let us also assume that the conditions in the body are such that the surface of each tissue is kept at a constant temperature Ts. Okay, this is quite common. The body has temperature control mechanisms by which it effectively maintains the surface of each tissue at a constant temperature. In this case, we're going to call it Ts. Let's say 37.3 degrees, 37 degrees, whatever. The normal body temperature, that is. And 38, okay, we'll see what that is. And that there is no heat flux along the tissue length. There is no axial heat flux. There is only a radial heat flux. Also assume that no other work is done by the tissue. The tissue is at rest. There is no other work. There is just the other aspects that are associated with the normal functioning of the tissue. In this case, a muscular tissue. Okay, the way we can approach this, now that we have the equation of thermal energy, is we go to the appropriate coordinate system, pick up that equation, cancel out the irrelevant terms, whatever remains is the governing equation for our case. Okay, that's the beauty of this. So we can go to equation B2, cylindrical coordinates. I've already shown you the table. I've requested you to make a copy of it. Please go to that table. Please see what B2 is. Okay. Can you pause the video here, go back, go to your table, pick out equation B2 and then restart the video, unpause the video. Go ahead, please. That equation B2 in table 4.2-1 for cylindrical coordinates would have been this: rho Cv dou T temperature time plus Vr dou T dou R plus V theta by R dou T dou theta plus Vz dou T dou Z equals K times 1 by R dou R dou T dou R plus 1 by R squared dou squared T dou theta squared plus dou squared T dou Z squared plus 2 mu dou Vr dou theta dou Vr dou R the whole squared plus 1 by R dou V theta plus Vr the whole squared plus dV dou Vz dou Z the whole squared plus mu times dou V theta dou Z plus 1 by R dou Vz dou theta whole squared plus, mu is a common thing here, plus dou Vz dou r plus dou Vr dou z the whole squared, plus 1 by r dou theta of Vr plus r dou r V theta by r, this entire term, okay, sum of these two terms squared, plus q dot other minus w dot other. Okay. So this would be the equation. So let us apply, or let us see which of these terms are relevant for our case. This balance is certainly relevant. So this represents balance, and we have taken this. So let's start. We are going to do a steady state analysis, therefore no time derivatives. This first term goes to 0. There is no velocity at all, there is no flow that is happening here. Therefore, the Vr, V theta and Vz components can be blindly put to 0 wherever they occur. Here, of course, temperature varies with r, that's the whole point here. Temperature does not vary with theta, there is angular symmetry. Temperature does not vary with z as mentioned in the problem. Or we can take the temperature not to depend on z, the axial distance. None of these terms would remain because each one of those has velocity of the fluid. Okay, Vr, V theta and Vz are the velocity components of the fluid. In this case, there is no fluid flowing. The blood is not a part of the tissue. Blood is not a part of the system that we have taken our focus here, and therefore we don't have to worry about the blood flow at all. Okay. Then these two terms will completely drop out. There is of course q dot other, right, because there is metabolic heat that is being generated as mentioned. That heat comes in, even though blood is not a part of the system. Those heat aspects coming into the tissue, that is fine, or being generated in the tissue, that is fine. That is being considered as a whole black box kind of a thing. Minus w dot other, there is no shaft work that is done in this case. So this is what the equation reduces to, and are we going to call it something? No. Okay, that is the balance equation. We have brought it down to the terms that are relevant to us in terms of the terms that are relevant to us. Q dot other is Qm dot metabolic heat rate that I already mentioned. Therefore, the only terms that are remaining here, all these have gone to 0. This term remains, of course. All these have gone to 0, all these have gone to 0. Here you have Q dot other, both on the same side, therefore they will be negative if you take it to the other side. So that is what has been done here, minus negative k by r d dr r dt dr. R is the only variable here, so the partial derivatives have been converted to total derivatives, equals ordinary derivatives, whatever you want to call them, equals qm dot. Okay, so this is the equation which describes whatever is happening. Equation 4.2.1-2. Now we need boundary conditions in, this is steady state. Boundary conditions to solve this, second order, therefore we need at least two boundary conditions to solve this. So boundary condition 1 at r equals 0, the center point, right, the same trick. So the temperature variation we are looking at, the temperature at the center point must be the same irrespective of the direction we take to reach the center. Okay, the direction is whatever we are taking. Whatever temperature profile is there is reality. So that reality should not be affected by the direction that we take or the approach that we take. That is the bottom line for expecting a certain behavior at the center. Mathematically speaking, this reality can be reflected only if there is a maxima or a minima in temperature at the center in a physical system. And if there is a maxima or a minima, the derivative equals the derivative of the temperature with respect to the radius has to be equal to 0. Okay, we know that. So r equals 0, t equals finite, or dt dr equals 0. Okay, same boundary condition that was first introduced in mass flux chapter and then also extensively used in the momentum flux chapter. We are going to use that here too. Equation 4.2.1-3. The boundary condition 2 is quite straightforward. At the surface at r equals r, the temperature equals the surface temperature Ts. 4.2.1-4. Therefore, if we integrate 4.2.1-2, this equation with the boundary condition 1, dt dr equals, at r equals 0, dt dr equals 0. And you substitute, if we first integrate this, you know that if r dt dr, if you integrate once, you take this becomes qm dot r by k, a minus also, and d dr of this equals qm dot r by k. Now you integrate that, you'll get r squared by 2. There's already a r there, so that one will go away, and you get dt dr equals minus qm dot by 2k times r. And if you use the boundary condition 2 at r equals r, t equals ts, then we'll get the constant of integration as t equals ts plus qm dot capital R squared by 4k times 1 minus r by r squared. Okay. We're going to call this equation 4.2.1-5. Does this remind you of something? Okay. When we started out this lecture, I did mention watch out for some similarity with something that we've already done, especially this term and somewhat this term and so on and so forth. Do you see some similarity? Yeah, it is with laminar flow in a cylindrical pipe. The velocity distribution is a function of 1 minus r by r squared, a parabolic velocity distribution. Okay. So in this case of pure conduction, right, in a muscle, the equivalent of this laminar flow in a pipe for the momentum flux case, we have a parabolic temperature profile similar to the parabolic velocity profile. Okay. And this is the entire temperature profile. Of course, you have a Ts and so on and so forth. Okay. Now, let's non-dimensionalize the solution to make it more generally applicable. So we'll define a theta, a non-dimensional variable, as t minus ts divided by qm dot r squared by 4k. You work out the dimensions, it will turn out to be dimensionless. Then we also called a xi, a distance variable, as r by the radius of the muscle, r, radius of the tissue. It's a muscle. The solution we already know, it's just the same form, the same solution as in the case of laminar flow through a pipe. The solution is theta equals 1 minus xi squared, 4.2.1-6. And therefore, if you plot theta versus xi, this is the value 0 for xi. This goes from minus 1 to plus 1, r by r. The radius at the center goes from minus r, we have converted to r by r into a distance variable, and therefore it goes from minus 1 to 1, and you have this nice parabolic profile here. Okay. So this is the temperature profile in out of pure conduction situation in a muscle, which we have assumed to be a cylinder. The rate of heat dissipation at the cylindrical surface for the tissue length L equals area times flux. Okay. If you are interested in the rate of heat dissipation at the cylindrical surface, which is a nice thing to know, which is nothing but the area 2 pi RL times the flux QR at R equals R. Okay. The radial flux at R equals the surface, 4.2.1-7. And this is nothing but minus k dt dr at r equals r, right? This is the flux from Fourier's law, one dimension. That is nothing but pi r squared L qm dot. If you calculate minus k dt dr from the temperature profile, either this or we can directly go to this in this case, get dt dr multiplied by k, and this term will drop out, this k will cancel, and so on and so forth. Whatever remains of this after derivative, if you plug it in here, you're going to get this as pi r squared, minus will go out, pi r squared L qm dot. Okay. So that is equation 4.2.1-8. Please try this out and see how this works out. And of course, it's quite easy to see that Tmax occurs where r equals 0, the center line, 1 minus r by r squared. So only when that small r is 0, which is the center line, can you have a maximum temperature Tmax. Therefore, Tmax is Ts plus Qm dot r squared by 4k. Now, if we substitute typical values, r equals 1 centimeter, reasonable value. Qm dot metabolic heat generation, 5 calories per centimeter cube per hour. Okay. It's nice to have thumb rule values. This is a nice thumb rule value. 5 calories per centimeter cubed per hour. Conductivity is 10 power minus 3 calories per centimeter second degrees C. Okay. All these are to the raised to the power of minus 1. And the temperature of the surface we're going to take is 37 degrees C. If you do this, your Tmax happens to be 37.3 degrees C. Okay, Ts is 37, Qm dot 5, all in consistent units here. Therefore, everything should cancel out to give you temperature. So, Qm dot r squared by 4 times K, which is this, and then there's a conversion from hour to second and so on and so forth. That's the reason why this 3600 comes in. 5 by 5, this 3600 goes with 5. Okay, this is calories per centimeter cube per hour. Therefore, calories per centimeter cube per second is going to be 5 by 3600. R squared is 1 squared, 1 centimeter, and 4 into 10 power minus 3, 4k. Okay. So, the units all cancel out, or you could convert them into all consistent set of units and then cancel out. It doesn't make a difference in this case. That will turn out to be 37.3 degrees C. Okay. So, the center point of the muscle is 0.3 degrees C higher than the surface. The maximum temperature is 0.3 degrees C higher than the surface temperature. That's the insight that we get from this. It's a nice number to have as long as your model appropriately describes your system. In this case, it does. Okay. I think we can stop here and continue in the next class. See you then.